Alright folks, this is the first part of the video for the end of chapter 16. We're going to review this slide. We have binary acids here. Binary acids are hydrogen attached to something else, and so we have a series here. We have HF, HCl, HBr, and HI, and so we want to think about the differences between these halides. We have fluoride, chloride, bromide, and iodide. And when we go down the periodic table, what happens? Well, as the one on the top is the smallest, and the one on the bottom is the largest. We add a valence shell each time, so we get bigger and bigger and bigger, and that hydrogen wants to interact with the valence electrons on that atom, the F, the Cl, the Br, or the I. So we have the largest on the bottom and the smallest on the top. Also, if we think about the halogens, as you go up the periodic table towards fluorine, we have fluorine with the highest electronegativity, and then iodine, which is also electronegative, but not as electronegative. So this is the lowest in the series in terms of electronegativity. So we have a really small atom that really wants to hold on to the electron, and we have a really big atom that doesn't necessarily want to hold on to the proton. And so here, if we think about a positive H plus and a negative F minus, because that H plus can get really, really close to the F minus, the bond is the strongest. So we have the strongest bond up here. In terms of Coulomb force, it's the charge, which all these have the same charges, but distance, and so its size depends on distance. So then we have a hydrogen H plus down here and an iodide minus, which the cloud, because it's bigger, this bond is enlarged, and the longer the bond or the further the distance, the weaker the bond. So the weaker the bond, here are our bond energies over here. For HF we have 570, and for HI we have 298. So the weaker the bond, the easier it is to donate the proton, which means the stronger the acid. Okay, so HI is the strongest acid in this series, and HF is a weaker acid. All right. So if we think about that same kind of process, but now instead of going down and up a group, we're going to go across a period. So we have carbon. Right, if you look at a periodic table, we have carbon. Then if you go one to the right, you have nitrogen. Then you have oxygen, and you have fluorine. So we already know that this is a weak acid. We just said that on the last slide. We know that HF is a weak acid. Let's think about how we classify these other things. Water. We classify that as a weak acid too. It could be a weak acid or a weak base. All right, and then NH3, well, we typically call that a weak base, right? So it's going to be more basic than acidic, but technically it could donate a proton, but not as efficiently as water, and especially not as efficiently as fluorine. And then we get to something like methane over here. Methane is a hydrocarbon, just hydrogens and carbons, and these are nonpolar bonds. There's no reason that the carbon would want to pull the electron density away from the hydrogen and weaken that bond, and so this is basically non-acidic. And so if you look at the acid strength series here, really what we're thinking about is the electronegativity of that atom. And so NOF is highly electronegative. It's going to pull electron density away from the hydrogen, and the acid strength goes up. So it's based on the electronegativity of that bond, right? The polarity of that bond. And now we're going to go to oxoacids. Oxoacids are acids which have bridging oxygens. Okay, they can have one or more. Here we're going to look at a series of acids that have one bridging oxygen, but the difference is the halide. So we have, again, I, a Br, and a Cl. And so these are in the halogen group. We're going up and down the periodic table here. And before we said it was based on the size of the atom, I mean, in the electronegativity. Well, here, because we have this bridging oxygen in each of these, right, there's a bridging oxygen here in each, the size of the iodide doesn't really matter anymore because there's a buffer between the hydrogen and the iodide. So here, it really just depends on the electronegativity. So chlorine is higher up close to fluorine, so chlorine is the most electronegative, and in terms of drawing dipole arrows here, you have dipole arrows that are getting increasingly bigger as you go up the periodic table, and you get to more and more electronegative atoms there. And so when you look at these Ka values, right, Ka is the biggest here, and the smallest here. And so these are trends that you can follow, and then medium here in the center. And it depends on the electronegativity of that outer atom there. Okay, if we go and think about oxoacids with many bridging oxygens, more than one, here we have to get into these suffixes and prefixes. If you remember, we have chlorous and chloric, and my mnemonic for remembering these names is lower has an O, and higher has an I, and there's ic, chloric, and chlorus in the name. And when you have more than two, then you gotta use the prefixes here. So we have hypo, like hypoglycemic, low sugar, so low number of oxygens, and then perchloric down here. We just add per to chloric to get the oxygen with, or the acid with 4 oxygens. So here what we want to think about again is the number of bridging oxygens. So the size of the chlorine doesn't really matter because they're all chlorines here. But if we think about the number of bridging oxygens, each time we add an oxygen, we're adding something that's electronegative. And electronegative things are going to try to make a partial positive one side and a partial negative on the other. And so here for chlorus, we're adding even more oxygens. The arrow is going to get bigger. And then we add for chloric, even another oxygen, the arrow gets bigger. And then finally for perchloric, we're getting a really, really, really big arrow here because we have 4 oxygens and 1 chlorine, all of them being electronegative, all pulling electron density away from this bond here. The more electron density that's pulled away from the hydrogen-oxygen bond, the stronger the acid. And so if we look at the Kas here, this one, perchloric acid, is one of the strong acids, so it's just very large, some huge number. And hypochlorous acid is pretty weak, 10 to the negative 8. And another way that you can look at this is by the oxidation number of the chlorine or the halide here. We could look at that. So if we start thinking about oxidation numbers, we've got a hydrogen, which is a +1. We've got an oxygen, which is a -2. Overall, this thing has to be 0. So the missing part of this puzzle is +1. So +1 minus 2 plus 1 equals 0. So the oxidation of chlorine is +1 for hypochlorous. If we add in another oxygen each time, we're adding a -2 charge, so that's going to make the chlorine have to be more positive by also 2. So we get +3 here, add 2 +5 here, and +7 here. Okay, so as the oxidation state of chlorine goes up, as the positive character of chlorine goes up, the acid strength gets bigger. Right? Chlorine is electronegative, it wants to have electrons. Oxygen is electronegative, it wants to have electrons. The more positive chlorine gets, the more it's going to want to take electron density away from that hydrogen-oxygen bond to be more negative. So either way works. You can think about it just in terms of electronegativity, or if you like trends with numbers, you can think about it as the oxidation number. All right, here's some examples of this. So go ahead and pause your video as you're doing these. Ask yourself, which one do you think would be more acidic in these pairs? These are a very typical type of question. So for A, we have H2S and H2SE. And so here we got to think about the difference in these two. The difference comes in selenium and sulfur. So look on a periodic table, look at the position of sulfur and selenium, and decide which trend you want to follow. Okay, so sulfur is above selenium on the periodic table, so we're in the same group, we're not across a period. So within the same group and having hydrogen directly attached, there's no bridging oxygens here, we want to think about size and electronegativity. And so sulfur is smaller than selenium. It's in the 3rd period versus the 4th period for selenium. So selenium is a bigger atom. The hydrogen is going to be attached to a bigger atom. They're roughly the same electronegativity, but sulfur is slightly more electronegative. And so the higher electronegativity and the smaller size is going to make the hydrogen want to stick to the sulfur more. It's going to be less dissociable. And so here the hydrogen is going to come off of the H2SE more easily. So that means that H2SE is the stronger acid. Strictly based on size and electronegativity. Okay, now we're going to go to the second, part B, HI or H2TE. So here again, we got to look at I and TE. And when we look at the periodic table, we see that they are neighbors to each other. So they're across the period, not down a group. So across the period here, they're about the same size. Now we got to think about electronegativity only. So we think about Hi and H2Te. I is going to be more electronegative. It's further to the right of tellurium, and that therefore I is more electronegative. And because it's more electronegative, it's going to pull electron density away from the hydrogen-iodine bond, and so therefore now Hi is the stronger acid here. All right, now we go to part C. We have HNO2 and HNO3, nitric acid and nitrous acid, lower nitrous. And now we got to think about the bridging oxygens in here. So the hydrogen is not directly attached to the nitrogen, but we have a nitrogen with 2 oxygens and a hydrogen attached to one of those, and we have a hydrogen attached to an oxygen nitrogen with 3 oxygens around it. So here we have oxoacids of differing numbers of oxygens, and so again, oxygen electronegative, nitrogen electronegative. So if we think about polarity of these two, we're going to have one which is a higher dipole arrow, and therefore this one is going to be pulling electron density more to this side than this one, and so it weakens this bond here, and nitric acid is going to be stronger. Nitric acid is also on the list of strong acids, and nitrous acid is not, so that should be a clue to you too. All right, part D. Here we have 2 things going on. So we have sulfuric acid, H2SO4, and sulfurous acid, H2SO3, and then we have H2SeO3. So here we got to think about analogs of each other. Okay, we have 2 trends going on. We have the trend here where we have differing numbers of oxygens. Okay, and then we also have a trend between these two where we have selenium with 3 oxygens or sulfur with 3 oxygens, and we have to decide which one is the stronger acid. All right, so let's do one at a time. Let's first look at trend number 1, and then we'll look at trend number 2. So between sulfuric acid and sulfurous acid, we got to think about which one has more number of oxygens. The one with more number of oxygens is more electronegative. It pulls electron density away and becomes a stronger acid. Also, we know that sulfuric acid is listed as a strong acid, and the first step is a complete dissociation step. So that means between the two, H2SO4 is a stronger acid than H2SO3. Now we got to think about trend number 2. So just like up above, we don't have a binary acid. We have it bound to an oxygen in an oxoacid, but sulfur and selenium, again, if you remember, sulfur is higher up on the periodic table. It's more electronegative than selenium. Size doesn't matter here because there's a bridging oxygen. And so sulfur is going to be more electronegative. It's going to pull more electron density away, and therefore H2SeO3 is going to be a weaker acid than H2SO3. All right, one last concept from this chapter is going to be Lewis acid-base theory. We had 2 theories already. We had Arrhenius acid-base theory, where acids were things that had H's that dissociate, and bases were hydroxides. Okay? And then we had Bronsted-Lowry theory, which was acids are proton donors and bases are proton acceptors. And that helped us with things like ammonia, remember? If you remember back, that didn't have hydroxide in its formula. And so here we have yet another definition, Lewis acid-base theory, where instead of saying we have a proton donor or a proton acceptor, we're going to call it, from the opposite side of viewing, an electron pair donor or an electron pair acceptor. So here we have that same reaction, ammonia. Ammonia has a lone pair on the nitrogen, and we have a proton over here with a positive charge. And so before, in Bronsted-Lowry theory, we would just say that ammonia is a proton acceptor. But now we're going to call it an electron pair donor. It's giving its electrons up to make the bond with the hydrogen, which is doing effectively the same thing. But you'll see why we have to make this distinction. So because it's an electron pair donor, it is a Lewis base, right? And because it was a proton acceptor, it was a Bronsted-Lowry base. So it's still a base. We're not changing that. This is a base. Okay, and we end up with ammonium cation on the other side. So electron pair acceptors are acids, electron pair donors are Lewis bases. Right, and here's where it becomes important. When you get a reaction like this, we have BF3, NH3, and if you think about boron trifluoride here, boron, if we drew a Lewis dot structure, has 3 valence electrons. Fluorines would come in and bond to each of these, and we would get B with 3 fluorines around it. And so this is a weird one that violates the octet rule. It doesn't have an octet of electrons because it only started with 3 valence electrons. And so if you look at its structure out here, we have, fluorines that are pulling electron density away from the center of the boron which doesn't have an octet, so we end up with a partial positive center and partial negative outer edge. And then we think about ammonia. Again, ammonia has this kind of a structure, okay, with a lone pair of electrons out here. And so we have a partial negative side of the molecule and a partial positive side of the molecule. And if you look at the combination of these two, we have a partial positive central area and a partial negative on the lone pair of the electrons. And so if you look at this electrostatic potential map, you get this perfect sort of coupling, lock and keys type of mechanism where you have stronger electron density and deficient electron density here and here, and these things can come together and form a bond, and we call this an acid-base adduct. Okay, so the lone pair on the nitrogen gets donated to the boron, which is deficient, and you get this acid-base adduct. And we couldn't describe this with with Bronsted-Lowry theory because we don't have a proton that's being accepted or donated. The only thing that's occurring here is that a lone pair on the nitrogen is being donated to the boron. And so we still consider this acid-base chemistry, and you see a lot of this in organic chemistry, which if you're moving on, you'll see a lot of these reactions early on in organic chemistry. All right, so let's look at another example. Here we have a Lewis acid and a Lewis base. This is SO3 and water. And SO3 is a gas, and sometimes we call it just SOX for generic, saying there's some number of oxygens there where X is a variable. But in this case, we're looking at specifically sulfur trioxide. And in sulfur trioxide, we have this Lewis structure up above where we have resonance here. This double bond here is kind of floating around all these positions, and we have partially negatively charged oxygens on the outside and a partially positive sulfur in the center. Then on water, we have lone pairs of electrons. We have a partial negative side of the water molecule and a partially positive side of the water molecule. So again, we can have a Lewis acid-base reaction where a lone pair on the Lewis base of water is donated over to sulfur, which is deficient of electrons. It's partially positive, and we form an adduct. Okay, and then we get here where these electrons get kicked out. Sulfur can't be hypervalent easily, and so they get kicked out to the oxygen. Then we have this hydrogen and oxygen here, which can then again act as a Lewis acid-base reaction and donate its electrons over to the hydrogen. The excess electrons here in this bond get pushed back to the oxygen, and you end up with this final product of sulfuric acid. This is what we call acid rain, if you've ever heard of that. So we used to use high sulfur coal and high sulfur diesel, and we would get these sulfur oxides out, and they would combine with water vapor in the atmosphere to make sulfuric acid, and this would cause acid rain. If you've ever been to a very old cemetery, you'll see headstones that are etched by acid rain, or if you've ever seen a marble sculpture or something that was etched by acid rain, kind of sort of loses its definition. And since we've stopped using high sulfur diesel and high sulfur coal, we have less acid rain in the United States, so it's less of a problem. Again, this is just a double Lewis acid-base reaction. We have a lone pair being donated from the water to the SO3, and then a lone pair from that oxygen being donated back. So we have a Lewis base up here. The oxygen acts as a Lewis base, proton donor, a lone pair donor, and the hydrogen acts as a lone pair acceptor, so it's a Lewis acid. All right, that is it for this chapter. Please go take a look at the video for the next chapter as well. Thanks.